Hello, I'm going to talk about our Capstone project. We are Group 10 in Section 1. Our Capstone project was about enhancing emergency room operations with Mimic 4 dataset. The ER system is projected to increase healthcare delivery efficiency while also contributing to data-driven decision-making by combining real-time patient tracking, medication reconciliation, diagnosis analysis, and other essential features. Using the Mimic 4 data can help ER operations better match patient needs, leading to improved outcomes and resource use. Traditional ER operations face hurdles in optimizing patient care and overall efficiency. We got this dataset from Boston Area Academic Medical Center to understand scenarios and hospital processes. Our goal was to develop a sophisticated system for predicting wait time in emergency rooms aimed to improving resource allocation and patient satisfaction. As we graph the distribution of waiting time in ER, the short wait times between 0 to 30 minutes were common due to efficient triage. Less frequent wait time between 30 to 200 minutes may be for treating less severe but urgent cases, and rare long wait time between 400 and 800 minutes are generally avoided due to potential worsening of patients' conditions, but could occur due to a high volume of patients or understaffing. As we graph the patient stay durations, there was a notable peak at around 5 hours, indicating it's a common duration for patient stays, with similar peak around 20 hours, suggesting common but less frequent stays of that duration. While longer stays beyond 70 hours decrease in frequency, likely due to their association with more complex or severe health issues, which are less common. Also, we graphed the word cloud of subject complaints and symptoms, which showed that the primary reasons for ER admissions were patients being transferred from one hospital to another or presenting with chest pain, followed by hyperglycemia and overdosage at the next most frequent causes.
For the machine learning part, we faced some challenges. We had some duplicates and null values. We have to fix this data in order to, this information in order to proceed with the machine learning modeling. We clean all the data, and we also did some encoding for some of the features. We had nominal features. We did the count encoding. For ordinal features, we use ordinal encoder, and Boolean features, we use one-hot encoding. We create the target, which is subtraction from chart time med record, and in time is the time where the patient goes to the emergency room and the time that it's being attended by someone in the staff.
So for our machine learning model, we went with other boost regressor, and we built three different models. So first, we actually made a correlation matrix with our target variable, that is wait time minutes. So we basically just did that to see if there was any correlation between the features, and out of that we found that med RN, respiratory triage, autosat triage, and SBP triage, these had some kind of correlation with our target variable. So from the first model we built, like where we took the four features from the correlation matrix, we got the mean squared error as 741, the R square as 93, and the mean absolute error as 15.77. So which was not too bad, because it just shows that there's around 15-minute deviation between the predicted and the actual wait time. So after this, we went ahead and we used grid search CV to see the best parameters for this model. And when we did that, we found that the best parameters would give mean squared error of 313 and the mean absolute error as 7, which is comparatively better. So, for the second model that we built, we decided to take in all the features of our data set and not just take like a few features. And we did that. And once we did that, we got the mean squared error as 876 and the mean absolute error as 19 and the R square as 92%. So once we did that, we decided to go for feature selection out of all the features that we had done. So once we went with the feature selection, we took the top features that had importance percentages that were exceeding. There were 5 and above. And a few of the features that we took were chief complaint, DBP triage, pain triage, SBP triage, temp triage, NDC, disposition, race, autosat triage. Now, compare this to our correlation metrics, we didn't really have any kind of categorical variables. So, here in this feature selection, we have categorical as well as the numerical variables. So once we created a model with these selected features, we got the mean squared error as 829, mean absolute error as 19.20, and the R square as 92.7%. So on this, we did hyperparameter tuning using grid search CV. So once we did that, we got the mean squared error as 65, the mean absolute error as 1, and the R square as 99%. So once we got these results, we went back and put these parameters again, and we got the model with the same kind of results, and we use this model to go ahead with our deployment, and the deployment will be spoken about by Perlin. Thank you.
Hello everyone, my name is Perlin Pereira and I'll take you through the deployment phase. Now starting with deployment, we have used Pickle to serialize our model. This simply means our complex machine learning algorithm is now a single Pickle file, that's model.pickle, making it super easy to load and use for predictions without retraining it each time. Our model is integrated into a Flask-based web application. This setup is perfect because it lets healthcare professionals input data through web forms and get immediate predictions on patient flow and risk levels. It's user-friendly and efficient with two main endpoints, the home route for data input and the predict route for showing those crucial predictions. And if something goes wrong, our error handling ensures that users get clear feedback on what needs to be fixed. So now let's switch over to the web application that houses our model. This is built on Flask and it's where the magic happens. It's user-friendly and built for the fast-paced environment of an emergency department. So now let's enter some data as if I were a healthcare professional at the ED. You can now see how the model takes that data through web forms and returns predictions. If I try something that doesn't fit, like entering an incorrect value, the application is designed to handle errors with ease, providing feedback without any technical headaches. Now on to recommendations. Our model is not a standalone solution. It works best when combined with the pre-arrival information such as the patient's chief complaint and pain level gathered by EMS in the field. This proactive approach allows the ED to get a head start on resources and personal allocation. Predictive modeling and risk stratification also play a key role. They enable us to manage resources effectively and ensure that patients with higher risks are attended to quickly. But it doesn't end there. We also emphasize the importance of continuous improvement through regular model updates fed by the latest data. Now, in conclusion, integrating machine learning into the emergency department is about more than just cutting down wait times. It's about supporting healthcare professionals with valuable insights and predictions, complementing their expertise. However, as we move forward, we stay vigilant, continuously evaluating and refining our model to ensure it remains accurate and relevant. Thanks for joining me with this brief rundown of our project. With these tools and approaches, we are not just changing emergency healthcare, we are setting a new standard for it. Thank you.